Thank you so much for joining us, and thank you to the IAU Workshop organizers for inviting us to share our work at this session. So I'm going to be talking today about astronomy data visualization using two software packages called WorldWide Telescope and GLUE, and in particular, how to use these in an educational context. So I and most of our team are at the Center for Astrophysics, Harvard and Smithsonian, with team members also affiliated with AAS and University of Illinois Urbana-Champaign. So I am the project director for the WorldWide Telescope Ambassadors Program, and I'm also the science PI for a new NASA-funded project called Cosmic Storytelling with NASA Data. Alyssa Goodman is the PI for both of those projects, and I've listed here our colleagues who are primarily responsible for the work that I'm going to show here, and this is funded by NASA. WorldWide Telescope is an astronomy visualization program that can be used on the web, and it lets you view astronomical imagery in context. So you don't just have an isolated image of a galaxy, but you can see where it's placed in the sky. You can see what constellation it's a part of. You can see how much of the sky it takes up. And there's many more features in WorldWide Telescope that I can't go through all of here, but I can just give you a little taste of some of the things that you can do with WorldWide Telescopes. So this is an example of a web-based interactive that is built on the WorldWide Telescope web engine through the open source code. And what we've done here is we've used the 3D solar system mode to build a solar system explorer. So you can use this to look at different objects in our solar system, and you can turn the lighting on and off. So you can teach things like night and day, you can talk about moon phases, you can talk about seasons, you can advance time. So you can make time speed up. This is now 100,000 times real time. So along with the WorldWide Telescope-based interactives, we've also written up lesson plans and student activity sheets that you can access at a PBS Learning Media website that's linked here. And there's also an interactive for the life cycle of stars, and there's another one for the expansion of the universe. Okay, so what is GLUE? GLUE is software that lets you link different representations of related data sets. And so as you can see in this clip, these views are interactive, and that promotes what's called exploratory data analysis, where, for example, if you notice that there's some outliers here, you might wonder, gosh, well, I wonder if there's something different spatially about those points that is causing them to be these outliers. You can select them here, and then the corresponding points are highlighted in all of your other views because the data sets and the views are linked together by common features in the data sets. So this technique is called brushing and linking, and this is a technique that is used extensively in data science, and these are practices that we want more people to learn how to do. So that is the motivation behind our new project called Cosmic Storytelling with NASA Data. And this is part of the NASA Science Activation Program. And the goal is to merge WorldWide Telescope and GLUE to create web-based learning resources to teach data science to the public. And we want to do this through a lens of storytelling. So for example, we want people to really think about how science ideas have changed over time as we get more or better data or learn to explore our data in different and new ways. So our first data story is, this is our prototype, this is just year one of the project. So none of this is available yet, but hopefully it will be sort of by the end of the year. So we are situating our prototype about the Hubble law in its historical context. So here are Edwin Hubble and Henrietta Leavitt, and we're asking students to imagine themselves as an astronomer in 1929, when the prevailing worldview was that the universe is static and unchanging. And it was a real paradigm shift when Hubble made this discovery that the universe is actually expanding and therefore started at one point, Big Bang. And So we want students to learn about this by diving in and making their own measurements and collecting their own data. So we're going to give them access to galaxy spectra data. This is from the Sloan Digital Sky Survey, and they're going to be able to use the spectra to determine velocities for their galaxies. And then they're going to use views in WorldWide telescope with HST image overlays, where they're going to use a standard ruler approach to estimate the distance to the galaxy. And what we're going to have them do is just make a really basic assumption that galaxies are about the same size, and we know how big the Milky Way is. And therefore, if we see another galaxy and we assume it's the same size as the Milky Way, we can estimate how far away it is. So by looking at the angular size measurement. So the students are going to make those distance measurements, and we're going to ask them to do this for, say, 5 galaxies, and then they can fit a line to their data points, and this is going to give them a value for a Hubble constant, which if you invert, it then tells you how old the universe is. So besides the whole historical context, we also want students to think about answering a big question for themselves. And so for the data part of this, we want them to really think about, if this is something that people don't already know the answer to, a lot of science labs involve recreating things where the answer is already known. So students don't really get to dive into the concepts of, if I'm measuring something where I don't know the answer is, how do I know whether my result is reliable? So that's something that we're going to kind of build into the data stories. And so for this one in particular, for example, we're going to have students do their 5 measurements, and then we're going to merge all of the data from their whole class and have them fit the linear function again and see that they may get a different value for their Hubble constant and therefore the age of the universe if they're using all of the data collected by their whole class rather than just 5 random galaxies that they've chosen. So if you plot the distribution of individual students' values over many different classes, then you're going to have a very wide distribution of age estimates from student by student values from 5 galaxies piece. If you then instead take the class by class values from groups of 100 at a time, you'll get a narrower distribution, and this will help students have a more intuitive feel for how to deal with random uncertainties in their data. So those are some examples of some of the ways that glue can help the students think about data and uncertainties. And then, of course, we want to bring this back to the historical context, so we can also have them, now that they have a better understanding of what this plot means, then they can look at Hubble's data, or they can look at data from the Hubble Space Telescope Key Project or Supernova 1A data. There's, we can get them more into like the historical sequence and understand, okay, well, Hubble made this really important measurement, and conceptually, he discovered an important thing, but his actual values were systematically incorrect. And so the value of the Hubble constant and the age of the universe has fluctuated over the last 100 years or so. And so that gives students a feel for why we want to keep measuring things even though we think we know the answer. Okay, so I'm going to finish there. So resources and links, you can find information about the WorldWide telescope-based interactives at the Ambassador's website. We don't have cosmic data story materials up yet, but look for those soon towards the end of the year. If you have questions, you can email me. Thank you.